Let's look at some of the assigned problems here from section 13.3. Starting with problem number 7 was requested. Find the slope of the tangent line to the graph of the function at the given point. So our function here is f of x is 2x cubed at the point 2, 16. So the slope of the tangent line is the limit as h approaches 0. I'm going to use the h definition on this one here of f of 2 plus h minus f of 2 all over h. And again, the 2's both come from, that's our x coordinate. Okay, so now if we take those and we put it into this specific function, we're looking at the limit as h approaches 0 of 2 times 2 plus h cubed minus f of 2. You can go ahead and substitute that in if you want, but f of 2, they've already figured that out for us. If we can read coordinates of a point, that's got to be 16 all over h. All right, hey look, it's a binomial. We've got to take that to the third power. So hopefully we remember from Pascal's triangle, it's 1, 3, 3, 1 as our coefficients here. So hopefully that'll help us out. I'm going to leave that 2 as the coefficient out front here. I just want to take 2 plus h and cube that. So the first one here, a, in this case is 2. 2 cubed is 8. Plus, now we have to take 3 times 2 squared times h. Now hold on, I can write that a little bit better, can I? 2 squared is 4. 4 times 3. That'll give me 12h. Plus, then I need 2 to the first, I'm sorry, from Pascal's triangle, 3 times 2 to the first times h squared. Now again, I can combine those. 3 times 2 is 6. So that's 6h squared. And then plus h to the third. Let's distribute, shall we? So this will give me 16 plus 24h plus 12h squared plus 2h cubed minus our constant all over h. And lo and behold, well, we're not really surprised by this anymore, are we? 24h plus 12h squared plus 2h cubed all over h. And again, in our numerator, every single term has h as a factor, so I will factor that out. So I'll leave us with h times the quantity, 24, plus 12h plus 2h squared all over h. Reduce that down. So this becomes the limit as h approaches 0 of 24 plus 12h plus 2h squared. Now that we no longer have the risk of a denominator of 0, we can go through with direct substitution. So the limit as h approaches 0 of 24, well, that's going to be 24. The limit as h approaches 0 of 12h, that's going to be 0. And that one's going to be 0. The slope of that tangent line is a whopping 24. For problem number 11, they challenged us to take that a step further. Find the equation of the tangent line to the curve at the given point. Ooh, then graph it. Well, hey, we got graphing calculators. That's not too intimidating. So we're going to start off the same way here as we just did with number 7. We have to find the slope of the tangent line. So the slope is equal to the limit as h approaches 0 of f of, again, our x-coordinate here is 2. So this is 2 plus h minus f of 2 divided by h. Now, yay, fractions. We love fractions. Everywhere there's an x, we've got to substitute 2 plus h. So this becomes, in our lovely numerator here, 2 plus h over 2 plus h minus 1 minus f of 2. Again, we know that's the y-coordinate of 2 all over h. And that numerator could use some work, couldn't it? So this is the limit as h approaches 0 of 2 plus h over, that's what, 1 plus h minus 2 over, well, let's make it all look like it's got fraction, shall we? H over 1. I know it looks like I'm making it worse, but now if I consider, again, this entire expression here, there are 3 terms. We want a common denominator for all 3 terms. The common denominator would be 1 plus h. So I'm going to multiply the numerator by 1 plus h, and I'm going to multiply the denominator by 1 plus h. So I've written there, what I have written there in blue is just a really strange version of 1. Do the same thing to the numerator as the denominator. I'm not changing the value, I'm changing the form. So in our numerator here, again, if we multiply by that common denominator, that'll get rid of the denominator here. So that'll be 2 plus h minus, now if I distribute here, negative 2 times 1 will be negative 2. Negative 2 times h will be minus 2h. And in my denominator here, I'm just going to leave that as factored. H times 1 plus h. Again, if that's going too fast, rewind. Combining like terms in my numerator here, it's, oh my goodness. Zoom and zoom. H, negative 2h. That's negative h. Reduce. So this gives me negative 1 over 1 plus h. And again, at this point, I no longer have the risk of 0 as my denominator. I've reduced that, canceled those like factors. So now substituting 0 in place of h, this gives me negative 1 over 1. So that's the slope of the tangent line. Now again, the directions here were a bit different. They asked for the entire equation of that tangent line. Well, we were told it goes through this point. We've just determined what the slope is. Time for slope-intercept form. Y minus 2 is equal to negative 1 times x minus 2. we should get y is equal to negative x plus 4. That's the equation of the tangent line to that curve at that point. Okay, let's take a look at number 19, where the direction said, find the derivative of the function at the given number. So we're going to find the first derivative of f of x is equal to 1 over square root of x. Yay, square roots and fractions at 4. Okay, so all we're going to say here is we're looking for the derivative. Remember, we put that little slash mark there. So we're looking for the derivative of the function at 4, which is equal to the limit as h approaches 0 of f of 4 plus h minus f of 4 all divided by h. Notice, I've done something from the first section and the second section and now the third section, and the directions are different, but we start off with the exact same way every time, okay? I guess I need to come down here. I need more room. Oh, yes, let's go to purple. What's going on? The limit as h approaches 0 of f of 4 plus h becomes 1 over the square root of 4 plus h minus 1 over the square root of 4 all over h. All right, that second one there, obviously we can simplify that a little bit. So now what? Well, just as we did with getting rid of the fractions in the previous one, let's figure out the common denominator here would be, obviously, that square root of 4 plus h, but because of the simplification here, we need the 2. So 2 square root of 4 plus h. Now again, we're not using conjugates here. I'm just trying to get these things from a complex fraction, multiply everything by the common denominator, and get it down to a simplified fraction. So again, if we multiply 1 over square root of 4 plus h times 2 times square root of 4 plus h, the square roots will cancel, but now I picked up a 2. Here, for the second part, second term in the numerator, the 2's will reduce, but now I've picked up minus square root of 4 plus h. And my denominator, again, I'm going to leave that factored. Well, okay. I guess that's progress. We don't have complex fractions anymore, but we still have square roots. Did I mention not using the conjugate earlier? I mentioned that earlier because now's the time to use the conjugate. So now to get rid of this, again, it's more along the lines of we want to get rid of the square roots because we know with this h in the denominator, we can't do the direct substitution at this point. So we'll multiply by 2 plus the square root of 4 plus h, both numerator and denominator. And again, the idea of multiplying by the conjugate here, getting rid of the square root from the numerator, 2 times 2 will give us 4, minus square root of 4 plus h times square root of 4 plus h. will be minus 4 plus h. And this entire mess here of a denominator, let's see here, I guess I could call that 2h times square root of 4 plus h times the quantity 2 plus square root of 4 plus h. What a mess. How are we ever going to... Oh, look at the numerator. 4 minus h gives us negative h. Well, we can reduce this with that one. And even if you're skeptical at this point in time, that solves all of our problems. Because again, with that h as a factor in the numerator, we can't do direct substitution. Now what happens if we do 0 equals h? If we do the direct substitution, 4 plus h, that just, oh, come on, cooperate here. That just becomes a 4, and that one becomes a 4. So we have negative 1 over 2 times, now again, this is square root of 4, so that's 2 times the quantity 2 plus square root of 4 again is 2. Inside the parentheses, 2 plus 2 is 4. 4 times 2 is 8, times 2 is 16. It all comes down to that single number. The derivative of the function 1 over square root of x at 4 is equal to negative 1/16. Okay? The phrasing, the directions are different here, the applications are different, but the basic setup is the same. Now again, depending upon how complicated that function is, you really have to rely upon your algebra skills. Write out the small steps. Don't try and do too much of this in your head. Write it out. Don't lose a negative sign somewhere along the way. Write it all out. All right, for 21, I actually copied the directions this time. Find the first derivative, f prime of a, where a is in the domain of the function. All right, so we're going to approach this just a little bit differently with their definition of a derivative. F prime of a is going to be equal to the limit as x approaches a. Okay, so in this case, we're not setting it up with h approaching 0. We're doing x and a. So again, if you go back to what was in the notes there, that's f of x minus f of a all over x minus a. Now again, how do you know to do this one and we were doing the other one before and you said it was all this? No, okay, it's the same concept here, slightly different forms. If you remember back to the notes, rather than having this binomial, the x minus a in the denominator, that's where somebody along the way, I don't know if we blame that on Newton or Leibniz, that we replace that with a single term. It makes our denominator simpler, makes the numerator a little bit more complicated, but we can deal with it. All right, well, we can deal with this here too. The limit as x approaches a. Now again, we can't substitute a in place of x right now. That gives us a minus a, our denominator is 0. We need to work on some simplification. So we need f of x. Well, that's simply the original function here. So that's x squared plus 2x. And then we have to subtract f of a, which means we substitute a in place of x. So that gives us a squared plus 2a over x minus a. Let's get rid of that set of parentheses there. So this is the limit as x approaches a of x squared plus 2x minus a squared minus 2a. What have we been doing from an algebraic standpoint with all of these? Pretty much the whole chapter here so far. We're looking for a way to factor what's in the numerator so we can reduce that with a factor from the denominator. So again, that's why this was drilled into you from Algebra 1 and Algebra 2 and earlier this year with me. Factoring is such a huge deal. So x squared plus 2x minus a squared minus 2a. What? Did you notice that we have two squared terms? So if I'm just rearranging these, and I put the squared terms together, I put the first degree terms together, and oh, hey, look at that. Just those two have a common factor. So now we're going to look at this from the standpoint of factoring by grouping. Hopefully that sounds familiar. With my first pair here, well, this is the difference of squares, and this will factor down into x plus a times x minus a. For my second pair, again, 2 is a common factor, so I can factor out the 2, and this is x minus a. My denominator isn't going anywhere. Now, a little refresher here about factoring by grouping. If we had, I don't know, b times c plus 2 times c, hopefully you would all tell me that they have a common factor of c, and that would then leave us with c times b plus 2. Okay? Again, if you need to rewind the little purple stuff on the side there, what I'm trying to point out is they have a common factor. And what I've written in purple off to the side is just a shorthand version of what I have written on the far left there in black. From, again, the groups up top, I have this product minus this product. I have got it down to only two terms in the numerator, each with two factors. But they have a common factor of, I'm sorry, I almost forgot, the limit as x approaches a. In my numerator, I can say that this is x minus a times, now again, what happened here with the b plus 2? This first factor was left over, so that's x plus a plus, from the second set, 2. Again, if you need to rewind and rewatch that, this is not black magic, this is not voodoo, this is factoring. Boom, boom. The limit as x approaches a of x plus a plus 2. Well, as x approaches a, this first term, x, becomes another a, 2a plus 2. That's the expression. Again, this is a big difference here with the directions here compared to the first few. Using our limit as x approaches 0, that's usually going to give us just a single value. Now again, if you remember the difference in directions here, for number 11, they asked for the equation of the tangent line. So the whole limit as h approaches 0 did in fact give us a number, but then we took the extra step to write the equation. So here we got a number. Here we got a number for the slope of the line. We use that number to come up with the equation of the line. Here we came up with the value. In this case, we're looking for the expression. We're looking for basically a new function. So starting with this function, f of x is equal to x squared plus 2x, the derivative of that function becomes f prime of a is 2a plus 2. All right, I know, lots of questions. Let's keep practicing. The next problem was 23. Again, we're supposed to be finding f prime of a, where a is in the domain of the original function. So for now 23, our function becomes, so f prime of a is the limit as x approaches a of f of x minus f of a all divided by x minus a. So if we apply that to our lovely function here, we're dealing with the limit as x approaches a of 1 x over x plus 1 minus a over a plus 1 all over x minus a. Now again, our standard trick here, we have complex fractions, find our common denominator, multiply everything by that common denominator, which would be the x plus 1 times a plus 1 in both numerator and denominator. Now again, I don't want to distract you too much. If you want to skip over the purple stuff, that's great. Simplifying, multiplying, dividing all this stuff out. If we say had 4 over 5 minus 6 over 7 over 8 over 1, our common denominator would have to be 5 times 7 times 1. So again, that's how we're getting the stuff there in blue. So if we multiply here by 5 times 7 and multiply here by 5 times 7, for the first part of it here, the 5's would reduce down, and my numerator would then become 4 times 7. With the second one, it's the 7's that'll cancel, and I will get minus 6 times 5. And in my denominator, it's going to be 8 times 5 times 7 because nothing there reduces. Okay, so that's the exact same thing that I'm going to do here with our lovely function. That for this first fraction here, x over x plus 1 times x plus 1 over times a plus 1. The x minus 1 here and the x minus plus 1 there will cancel, and I'm going to get x times a plus 1 minus, okay, and the second term here is negative. So now multiply that blue it's the a plus 1's that'll cancel, and I'm left with an a times x plus 1. So that simplified my numerators and got rid of fractions. Now in my denominator, I'll have the x minus a times x plus 1 times a plus 1. All together, again, nothing canceled. So again, take a look at the purple, if that helps. Oh dear Lord, I hope it does. All right, so let's distribute, get rid of the parentheses and this negative sign. So this is the limit as x approaches a of ax plus x minus, I'm sorry, let's do that better. Distribute the negative a, so this will be minus ax. Gee, that sounds familiar. Minus a. Again, I'm looking for a common factor to reduce here. So I'm not going to get rid of those factors from my denominator. I'm going to take advantage of that. Well, at the same time, it kind of looks like I'm being lazy. And in my numerator, this simplifies down into x minus a, which matches up nicely with that first factor there. Which then gives me the limit as x approaches a of 1 over x plus 1 times a plus 1. And now if we apply our limit as x approaches a, this becomes 1 over a plus 1 times a plus 1. Well, wait a minute, we probably should simplify that into the shortest form possible. 1 over a plus 1, the quantity squared. And again, our end result here, the final product for these, for 23, just like for 21, was an expression. Not a number. We're not substituting any particular values. It's an expression. It's, in essence, a new function. 25, for the first part of it there, is just what we did with 21 and 23. If f of x is equal to x cubed minus 2x plus 4, find f prime of a. So f prime of a will be the limit as x approaches a of f of x minus f of a all divided by x minus a. All right, so for our lovely trinomial, oh, look at that. So this will be the limit as x approaches a of x cubed minus 2x plus 4 minus, now for f of a, that'll be a cubed minus 2a plus 4. Get rid of that set of parentheses. Sorry, I said x cubed and I wrote x squared. I apologize, and I did it again. X cubed minus 2x plus 4 minus a cubed plus 4a minus 4. And look at what happened to the constants. So somewhat similar to what I had a moment ago here. I've got two cubic terms and I have two first degree terms. So let's group those. So x cubed minus a cubed minus 2x plus 4a all over x minus a. So again, I'm going to put these into pairs and we'll factor those down. But this time, instead of the difference of squares, which of course can be factored, here we have the difference of cubes. And for this one, difference of cubes or the sum of cubes, both of them can be factored. Do you still remember that formula? Because it's tricky. Okay, our first term is x, our second term is a, so this factors down into x minus a. But then the second factor of the two is not really a simple one. It becomes x squared plus ax. If you have more than one variable, we just traditionally put them in alphabetical order. So if you have ax or xa, those mean the same thing. I'm just going with tradition here. So x cubed minus a cubed should factor down into x minus a times the quantity x squared plus ax plus a squared. Remember, it's the difference. The one and only negative term here comes in the middle of the binomial. Everything else is positive. And again, we're looking for that common factor of x minus a. All right, that's looking good here from that first set of parentheses. But now what about the second one here? Yeah, both of them have 2 as a factor, but if I factor out a 2, that'll leave me with negative x plus 2a. Oh, I'm so sorry. I have messed this up for a couple of steps now. I was so excited about the 4s. I'm sorry. This inexplicably became a 4 all of a sudden. It shouldn't be. I'm sorry for those of you that caught that and were saying, Mr. Mike, you screwed up. I'm sorry. Scream louder next time. I couldn't hear you. Um, Let me fix that. Okay, all better now. Sorry about that. All right, so I'm sorry. Back to the second set of blue parentheses here. Yes, 2 is a factor. I can take out the 2, but now it leaves me with negative x plus a, and that does not match up exactly with my denominator. Right terms, but the wrong signs. So instead of factoring this out as just a 2, in order to make this work out the way I'm hoping it will, I need to factor out a negative 2. So negative 2x divided by 2, that'll give me positive x. 2a divided by negative 2 turns that into negative a. And now we can reduce. Now again, we solved this. Can I just skip writing some of that out? So this is the limit as x approaches a of now x squared plus ax plus a squared minus 2. No more denominator, no more chance of dividing by 0. We go with the basic substitution here where a is equal to x. So this becomes a squared plus a times a plus a squared minus 2. Well, wait a minute. That middle term is an a squared, so we have a squared plus a squared plus a squared. That turns into 3a squared minus 2. really wish things would cooperate all the time. So there's our new function, 3a squared plus 2. Now we have labored long and hard to get to that point, and then, oh look, there's a part B, there's a part C. Part B should be really simple at this point. Find the equations of the tangent lines to the graph of the original f of x at the points whose coordinates are 0, 1, and 2. Well, what we have here in green, this f prime of a is equal to 3a squared minus 2. That is connected with what we had earlier. That's going to give us the slope of the tangent lines at any value of a, including the 3 that they're asking for here. Okay? So all this means is for the slope at 0, this will be f prime of 0, 3 times 0 squared minus 2. That's negative 2. The slope of the tangent line at 1 is f prime of 1, which is 3 times 1 squared minus 2. All right, now this might require a little bit of thought. 1 squared is still 1. 1 times 3 is 3. 3 minus 2 is positive 1. And the slope of the tangent line at 2. So this will be f prime of 2. 3 times 2 squared minus 2. Well, again, 2 squared will be 4. 4 times 3 will give us 12. And then 12 minus 2 will give us 10. And again, those are the slopes of the tangent lines. We need to know the coordinates of those points of tangency. So that means we go back to the original function. X cubed minus 2x plus 4. So again, we substitute 0 now, not into f prime of a, we substitute 0 into f of x. Let's see, 0 cubed minus 0 plus 4. So that means this is at the point 0, 4. Put that together with our slope of negative 2, and then we should be able to come up with the equation of the tangent line there. Pretty simple. Y is equal to negative 2x plus 4. And then we'll do the same thing for when x is equal to 1. 1 cubed is 1, minus 2 times 1 is 2. 1 minus 2, that'll be negative 1. Negative 1 plus 4 will give us 3. So that means this goes through the point 1, 3. With the slope of the tangent line being 1, you can do the y equals m, I'm sorry, slope-intercept form first. And then for the last one here, putting 2 into the original function. 2 to the third is 8 minus 2 times 2, which would be 4. So 8 minus 4 plus 4, well, that'll give us 8. And again, the slope of the tangent line at the 0.28 is a whopping 10. So again, point slope formula here, that should give us y is equal to 10x minus 12. All right, so how does this all look together here visually? So our function was x cubed minus 2x plus 4. And again, a lovely cubic function there. It changes directions twice, okay. Only one x-intercept, that's interesting, rather than three. So they not only wanted this graph, but they also wanted us to show the tangent lines here. So again, our first one was y is equal to negative 2x plus 4. Okay, so again, that was at our y-intercept, a negative slope. Okay, nothing all that surprising there. Our next one was y is equal to, again, we had a nice slope of x, 1 plus 2. Okay, and then our last one, we had y was equal a whopping 10x minus 12. So starting way down there and then coming up rather steeply. Yay, color. My answer key is not in color. That looks like a confusing picture. This one I think looks a little bit better. Let's go on to 29. Yay, word problems. The displacement S, measured in meters, of a particle moving in a straight line is given by the Department of Redundancy Department with the equation of motion S is equal to 4t cubed plus 6t plus 2, where the time is measured in seconds. Find the instantaneous velocity of the particle at time A, 1, 2, and 3. Well, that first part of it here is basically challenging us to come up with our first derivative again. So the velocity of the particle as a function of A, we're looking for numbers. We want the instantaneous velocity. We want a number to describe how fast this particle is moving at a particular moment in time. If we're looking for a number, not a new function, not an expression, not an algebraic equation, I'm going to go back to the limit as h approaches 0 way of looking at things. So this is going to be s of a plus h minus s of a all over h. So we're looking at the limit as h approaches 0 of, oh, now isn't this going to be fun algebra? 4 times a plus h cubed plus 6 times a plus h plus 2 minus the quantity, I'm going to put that in parentheses, 4a cubed plus 6a plus 2 all over h. So we're going to take the a plus h and expand that with hopefully a lovely binomial theorem, and then we can just distribute the 4's, right? So this will be 4 times a cubed plus, remember Pascal's triangle, 3a squared h plus 3a h squared plus h cubed. And now I'm going to, yeah, we can distribute that in a moment here. I'm going to get rid of the rest of these parentheses by distributing. So this will be 6a plus 6h plus 2 minus 4a cubed minus 6a minus 2 all over h. Wow. Now I distribute the 4, so that'll give me 4a cubed plus 12a squared h plus 12a h squared plus 4h cubed Yay for a digital pen. Look at how much paper that would take up. All right, time to start slashing things here. 4a cubed, negative 4a cubed. Positive 6a, minus 6a. Positive 2, negative 2. Again, if we've done this properly, okay, screwed up last time, each of these terms in the minus f of a, or s of a in this case, those should all match up with and simplify and disappear. So this now gives me 12a squared h plus 12a h squared plus 4h cubed plus 6h. Again, don't lose that guy over there. H is a factor. So that'll knock that down to 12a squared plus 12ah plus 4h squared plus 6 all over h. Slash those away. So we get 12a squared plus 2ah plus 4h squared plus 6. And the limit of that as h approaches 0 is simply going to give us 12a squared plus 6. Because again, this will turn into a 0 and that'll turn into a 0 as h approaches 0. So we just have these two terms. Now again, this is velocity, so you may hopefully not be confused too much here. They gave us units of measurement. This is measured in meters per second. So just writing this out here on a nice clean page where I got more room. V of a, the velocity of this particle at any value of a is going to be 12a squared plus 6. Now the next part of it there asked you to find velocity at 1 second. 12 times 1 squared plus 6, that'll be 18 meters per second. Velocity after 2 seconds of measuring it. 12 times 2 squared plus 6. So that'll give us 54 meters per second. Yes, that's a 4. Deal with it. And then after 3 seconds, this rapidly accelerating particle is 114 meters per second. That's all we're doing. So with that first part here, we built the new equation, and then for the next ones, we're just substituting. We're applying this new function to come up with the answers to the specific values. All right, let's try 31. Again, a very commonly requested question. Roast turkey is taken from an oven when the temperature has reached the FDA approved 185 degrees Fahrenheit. It is placed on a table in a room where the temperature is 75 degrees. The graph shows Newton's law of cooling. Yes, you cannot get away from Sir Isaac, um, credited as co-inventor of the calculus. This is called Newton's law of cooling. That, yeah, you take the whatever the hot object is. I like the fact that they changed this to roast turkey. Most frequently, it's a hot cup of coffee or a wee spot of tea. Um, it's going to cool off, but it's not going to go down to zero unless you're putting it outside in the winter where the temperature out there is zero. It's going to cool off where the room temperature acts as an asymptote. Okay, so what do you see there at point P? It looks like, okay, after a time of 60 minutes, the temperature of the bird is approximately, what, 125 degrees? They're asking us to find the slope of the tangent line. If, okay, we can come up with the coordinates of the point of tangency, that really doesn't help us when it comes to slope. For slope, we need the coordinates of 2 points, okay? So now, I don't know how much did you copy it? Did you zoom in? How closely can you see that graph? Okay. The authors of the book are suggesting that if we go back to say 30 minutes after the bird came out, it had a temperature of 147. Another point that appears to might possibly be on our tangent line is after 90 minutes, the temperature of the bird is, they're saying, down to 106. Now, were your estimates for those coordinates the exact same as the authors? I'm highly skeptical. Okay? If you said, okay, after 30 minutes, that looks to me to be 150, and after 90 minutes, it looks like it's cooled down to 100 degrees, I'd take that. So now that we have A and B, forget about point P, forget about that actual point of tangency here. We need a secant line. We need 2 points on the line to determine the slope. So now 150 minus 100 over 30 minus 90. So that's about 50 degrees every 60 minutes. Oh, that's negative. So it's cooling off. No kidding. At that point, it's cooling off at about negative 5/6, or you could just say it's cooling off at a rate of 5/6 of a degree per minute. Now, by using these numbers here, all right, that's approximately 8333333. The authors of your book came up with a decrease, again, the rate of change with respect to time there, um, of 0.7. All right, so if we use these, again, I'm not sure how they're saying, how they're expecting that you should get those. Again, it's not a parabola, it's not a line. We're looking for the slope at that point of tangency. As long as you came up with something in the ballpark there, I'll be happy with it. All right, let's wrap this up with number 33. Tank holds 1,000 gallons of water, which drains from the bottom of the tank in half an hour. Values of the table show the volume of water remaining in the tank, measured in gallons, after amount of time measured in minutes. Find the average rates at which the water flows from the tank for the time interval from 10 to 15 minutes and from 15 to 20 minutes. All right, so for the first time interval, well, the slope there, let's see, at 15, it was 250. At 10, it was 444 over 15 minus 10. So that'll give us negative 38.8 gallons per minute. For the second time interval, we're going from 15 to 20. So at 20 minutes, it was 111. 15 minutes to 250. 20 minus 15. Again, it's a 5-minute interval, but now, look, it's not the same. Sorry. 27.8 gallons per minute. It's not a constant rate of change. So what they're asking you to do in part B here is estimate the slope of the tangent line at that point by averaging the slopes of the secant lines that we did in part A, which is really the derivative. So if we take the negative 38.8, add the negative 27.8, divide by 2, because that's how you find an average, we'll get negative 33.3 gallons per minute. And I've talked enough. Okay, so again, take a look at this, review that, rewind, review it again. When you're ready, I promise the quiz isn't going to be as tough as you're dreading. Okay, then take a look at the quiz and do your best. Good luck on that.